my great pleasure to introduce Dan Tehrani, and he will give us an introduction to client-side zero-knowledge proofs. Take it away.
Hello everyone. Who here owns a WorldCoin ID? World ID from WorldCoin. I guess no one or no many.
One person.
One person maybe. And who here owns an Ethereum address? Yeah, basically everyone, I guess. In our research, we want to enable zero-knowledge proofs to all of you who own an Ethereum address, rather than an approach taken by something like WorldCoin, where they create a new identity stack that is zero-knowledge friendly. But we think that there is a lot of things that we can do about with the on-chain state, with existing ECDSA, especially ECDSA keepers, and enabling generating zero-knowledge proofs with existing keepers could have many applications. And in this talk, I'm going to talk about the status of the research for enabling zero-knowledge proofs for existing identities, mainly Ethereum accounts. Okay, so I'll start with the motivation and talk about the solutions we have built so far, and then about things we're working on, and then talk about open questions. So first, what do we even mean by client-side ZK, and what's the motivation there? As I said, there are several paradigms when it comes to using zero-knowledge proofs, not for scaling blockchains, but for actually doing zero-knowledge stuff. And one is using snark-friendly keys, for example, baby jub keepers, which I think is done with many ZK applications, and having a dedicated identity stack for that. And another is using keys that exist in crypto wallets, like ECDSA keepers in Ethereum. And the goal is to do this simple thing. A user makes these zero-knowledge proofs about a zero-knowledge proof pipe that says something about the on-chain state. And most of the time, the proof consists of something like a membership proof, which obscures the identity of the user while preserving the credibility of that user. So in short, what we are aiming for is a credible nuance, which is a credible nuance from blockchain state. For example, some applications, example applications are like HeyNown, which you can give feedback to DAO proposals without revealing your Ethereum address. So you only need to prove that you own a particular NFT. And another interesting example, potential application, is relation discounted quadratic funding, which is like one really specific example of using zero-knowledge proofs. But I believe it's an interesting application to explore. In quadratic funding, in a variant of quadratic funding which uses pairwise matching, you want to prove that you have like this relation with other voters or other funders, but you don't want to reveal your identity. You want to fund or vote to a proposal or to a fund anonymously, so you can generate a membership proof or like a proof that the pairwise coefficients were calculated correctly. So in our research, we aim to enable these kind of applications. And yeah, next I'm going to talk about what kind of zero-knowledge proofs we need to enable those kind of applications. So what we aim for is a proving system that has a really small public parameter. In other words, the proving key should be pretty small, and fast proving, obviously, and reasonable communication, and the verifier complexity could be. It doesn't have to be like ON or login, because we don't aim to directly post these proofs on chain. We could compress that with like really stronger prover later on. So the verifier complexity could be ON or sublinear, but yeah. And let's see. And like really broadly, there are two kinds of zero-knowledge proofs that have applications in client-side ZK. One is a bespoke solution, like which uses primitives like ring signatures for membership proving, which is, for example, what ZK does. And another is just all other proving systems that we talk about every day. Gauss-16 NP-complete proving system that can encode any NP statements. And in this talk, we'll focus on working with the NP-complete ones, because for some applications, like really high expressiveness, including proving the knowledge of a premesh of a hash function is required, which is not possible with bespoke solution like ring signatures or other primitives. And we also want a field flexibility, which like in zero knowledge proving systems, we often need to do wrong field arithmetic when we are working on curves like BN254 or BLS 382 BLS. But in existing systems, these kind of curves are used, SecB, SecB to physics K1 or SecB to physics R1, and we want to encode operation in these fields natively. So we want to do right field arithmetic using these curves. And so that was like the requirements that we want and what kind of ZK proving systems that we were aiming for. So what do we have now? What kind of solutions we have now? Spartan ECDSA is a scheme that we've been working on for proving membership in an ECDSA public key group, and it makes significant improvements in proving time compared to solutions that came before it. And Spartan ECDSA encodes statements in R1CS over the scalar field of the SecQ to 5060 K1 curve, which is a curve that forms a cycle with the SecP curve. So you can encode SecP base field operations natively without doing any wrong field arithmetic. And the circuit for proving validity of an ECDSA signature and including that is included in the depth 20 binary Merkle tree, results in about 8,000 R1CS constraints. With some, this 8,000 R1CS constraints is a result of another like ECDSA optimization, which I won't talk about in detail here. But with this proving system, a proof can be generated in about 4 seconds. So this specific circuit, specific like a predicate, you can generate a proof in about 4 seconds in browser, which is a significant improvement compared to doing wrong field arithmetic. I think, some of you know that generating an ECDSA proof will take like 10 minutes or impossible in a browser if you do wrong field arithmetic with Gauss-16 or something. So now we have this scheme that you can generate a proof in a reasonable time. But this specific circuit with 8,000 or so constraints doesn't include the Keccak hashing of the Ethereum public key, which we think is okay because public keys can be extracted from past transactions. So we can create a group of Ethereum public keys instead of creating a group of Ethereum addresses by simply extracting public keys from the transaction history of the addresses we're interested in. So we don't do the Keccak in our circuit because Keccak is just brutal for browser proving. And so we have this like basic proving time improvement. And so what kind of things are missing to enable more applications to flourish? There are actually a bunch of things that are missing. This is likely not all of it, but for this talk, I will focus on on-chain verification and recursion, which I hear the most demand for. First, I want to mention that recursion is not only for scaling proving system, but it could be a primitive that could play a role as a pretty high-level building block for a certain set of applications. For example, ethos is an application that lets you prove your degree of separation from Vitalik, and it uses recursion to pass on proofs. So you can build the proof that you're this degree separate from this person by proving the validity of the previous proof, and also proving that you own a signature that is signed by that person who passed you the proof. And so going back to on-chain verification, for Spartan ECDSA, the proofs are pretty large, so directly posting them to like chains like Ethereum is likely not an option we have. This phenomenon of proofs being large in client-side ZK is pretty natural because considering that we don't want to let the users compress the proof, we don't want to make the users compress in proofs. We only want to let them blind the witness and then just let the compression done by like other remote provers. So the proofs being large are pretty natural, and we do think that even if we come up with something other than Spartan ECDSA, the proofs will be pretty large. So the general paradigm for verifying proofs on-chain for client-side client-side ZK will probably going to look like this, where the proofs are large. The proofs generated by the users are pretty large, and in order to post them on-chain, we want a stronger prover that compresses the proof, and then pass that to the weak prover like Ethereum or any like blockchain. And to get more scale, we want the strong prover to work as an aggregator that aggregates using techniques like recursion to compress multiple proofs into a small proof. So how can we actually do this recursion? First, recalling that we want the system to work with all finite fields and that we're actually doing zero knowledge. So we're operating under different set of assumptions compared to systems like ZKVMs. Several systems construct aggregation schemes, for example, Nova, Supernova, Halo 2. There are multiple strategies due to recursion. And currently we're working on the Halo 2 verifier of a Spartan proof. So basically compressing a Spartan ECDSA proof with Halo 2, which uses a variant of a Halo 2 that uses KGZ as a backend, so we can post the proofs on-chain. And we should get that benchmarks pretty soon. And given these recursion strategies, we believe there are these two primitives that might be important when building a recursion aggregation strategy for client-side ZK. One is ECFFT, and another is the folding scheme. First, ECFFT, or elliptic curve fast Fourier transform, is an algorithm for doing FFTs in all fields. To briefly go through the algorithm, let's FB be the field we want to work on. Maybe this could be the SecB base field for ECDSA. And we find an elliptic curve in that field with an order of some power of 2. And we use a degree 2 isogeny to map elements in that elliptic curve we find into another elliptic curve with half the size. And this degree 2 isogeny can be substituted for the squaring operation in the FFT algorithm. So this allows us to do FFT in all finite fields. And as I think many of you know, most of the proving systems require FFT. So having this ECFFT algorithm, we could modify Planck or any other proving system that uses FFT to work with all finite fields, which is really, really powerful. Yes, and it works for Fry as well, which uses ECFFT a little different from it is used in FFT. But Fry has this like analogy to FFT, which like folds the operation every time in half, and you can do similar techniques using as ECFFT to make Fry work with all finite fields. So in theory, we can do Fry in SecB, which could be really, really powerful, considering that we might be able to do, we could do a Starks over SecB or something. But ECFFT, as far as I know, there are no any deployments, and the concrete performance is still yet unknown. So yeah, even though this scheme is actually pretty simple, some additional work is required to get this to production and get the benchmarks. Another primitive that could be interesting and important in recursion for client-side ZK is the folding scheme. To go through it briefly as well, The folding scheme, specifically the one used in Nova, works as follows. First, to set the notations, a classic R1CS instance consists of 3 matrices, A, B, and C, and the witness W, public input X, and concatenating them, we have the vector Z. And yeah, and the ABC matrices should satisfy with W should satisfy the relation. And in Nova, we fold 2 relaxed R1CS instances, which is a variant of R1CS that is defined in the Nova paper, by introducing a bunch of variables. But the core idea is to take the random linear combination of 2 Z vectors and fit that into the R1CS equation. So even though we have 2 instances, we can check them as we're checking only one. And that's the basic of the folding scheme described in Nova. And the prover or aggregator in our context snarkifies the equation in Brown and posts the snark on chain. So we still need to aggregate, we still need to snarkify this equation, and we still need to let the aggregator know what the witnesses are in this specific example, what W1 and W2 are, in order for the aggregator to actually create the final snark. But in our context, we want to hide W1 and W2 from the aggregator, because the aggregator is the powerful prover that sits in the middle of the user and the chain. So we cannot directly use Nova-like folding scheme for client-side ZK. But the ideal flow, just to define the model, is it's basically like this. So weak prover is the users, and every users submit their witnesses WI, blinded witnesses WIs to the strong prover, and the strong prover basically folds those witnesses and then produce the final small proof pi that can be verified on chain. This is the ideal flow, but we still don't know if we can make this if we can make this an efficient system. So we still don't know if we can introduce this like blinded witness while preserving the efficiency of Nova. But yeah, it's definitely an important direction to explore, and we have some ideas, but they're not ready yet, and they're not definitely concrete. So I will not talk about it in this talk. So to conclude, we have some basic proving some improvements that let us build some applications, enabling credible new ones. But there are a large set of applications that we can't build because we don't have nullifiers, which I didn't talk about in this talk, but it's also an important primitive in client-side ZK. And if you have questions about it, definitely I can answer. And then if you have any thoughts on it, I would like to talk to you with it about it. And there are also a lot of unknowns. On-chain verification, we still don't know what kind of strategy is best, as I talk about. One could be fry with ECFFTs, or a folding scheme like Nova, but modified to preserve zero knowledge. And also, recursion could also be, it might be the case that in some kind of use cases of recursion, for example, like in ethos, which uses recursion as a really high-level building block, we might want to use one particular recursion strategy. But for on-chain verification, we want to use another strategy for recursion. So there might be this different trade-off space in designing recursion as well. So that's another interesting topic to look into. And finally, even though we have we have our Ethereum addresses, we have our public keys, we don't know what the identity stack will look like in the future, especially after things like account abstraction gets adoption. So yeah, as always, a lot of problems to solve, and yeah, fun and exciting work ahead of us, I guess. And yeah, that is all. Thanks for listening.
Thanks a lot. Any questions? Yeah, can you hand the mic over because I can't walk through.
Yeah, I want to know why the weak prover cannot just aggregate a proof in the blockchain. Like,
So let's see. Let me just show you this slide again. So I think you're talking about this, right? So the reason why we can't aggregate the proof, the weak prover cannot aggregate a proof. It can, but it will require a lot of proving time, because in order to process it on chain, we want the proof to be small. So either like constant size or logarithmic size. But in order to let the prover generate proofs efficiently, we can't make the prover, we can't require the weak prover to do the compression work. So in order to post it on chain, we need to have this intermediate strong prover.
so it's more about the gas concern then.
Yes, it is, yeah.
More questions?
What's your intuition for how, like where finality will be from the perspective of the end user, like the browser, the weak prover? Will they think that it's done and like is it good enough for most use cases that they send it to the strong prover, or is it going to be once the strong prover does fold those proofs and puts it on chain?
Finality, you mean like on L1?
Like in a use case where you're doing this, for, I guess for hey announce, you know, the timeline doesn't matter so much, but then when you get into use cases that are more and more latency sensitive, do you think that the trust involved in the strong prover is going to basically prevent some use cases, or will that be efficient enough to?
Yeah, that's a good question. We still don't know, and I think it's pretty. I think the time that we face that problem will be pretty ahead of us. But yeah, certain types of applications won't be possible due to the latency. But we believe many ZK VMs and ZK rollups will use recursion strategies. So I think that sequencers, like simple L2 sequencers, will have similar latency problems. So I don't think this is a specific issue for aggregating the knowledge proofs, but just like having a sequencer or an aggregator or like recursive prover, I think most of applications will have similar issues.
In terms of like, you've got the aggregator, which I assume is like posting information on chain, right? In terms of the kind of gas costs, does that leave you exposed as Personae Labs to fluctuations in gas, or are you covering that somehow?
Definitely we'll have issues with gas costs, but one thing to note is that we don't need to post our proofs on L1 because we're not doing like roll-up stuff. We're not roll-ups, we're just trying to, in order to interact with other like smart contracts, and for example, any blockchain, it could be Ethereum L1, but it could be L2s, Optimism, or Arbitrum, those kind of stuff. In order to interact with that, we want to post it on chain. So it could be the case that for many use cases that use zero knowledge proofs, client-side zero knowledge proofs will have their smart contracts on like L2s, like Optimism, or even like Validiums that have really cheap gas cost. So definitely we'll be affected by gas costs, but there are many like chains that we can post them to, and it will depend on the chain, I guess.
I wanted to ask you something related to the prover key size that you were mentioning that it's an issue. There was a similar thing in a ZK Bridges application. There was Succinct Labs, they built something where they did not use the public key itself, but it was the hash of the public key. And do you see any scenario where you could actually, you don't really actually have to download the public key, but perhaps it needs some properties. The hash must be additively homomorphic or something like that. So in order for it to work?
So the public key here, most of the time it will be simply the circuit itself. So we want the user to, so the proving system that encodes statements in R1CS, we need the user to download the actual R1CS to generate the witness, and then, So most of the time, the proving key will be just the circuit. So
it's huge.
Yeah, it could be used, but for example, in Spartan ECDSA, it's like 5 megabytes or so because it's only 8,000 constraints or so.
So you do need like a very lightweight circuits for this.
Yes, exactly. If we go to like 100,000 constraints or something, it's still, I guess, like several, like, I don't know, 10, like 30, 40 megabytes or something. It's not impossible to download, but if yeah, we kind of have to expect users to have good bandwidth internet. And yeah, the download time could be pretty long, so.
Yeah, I'm just wondering because sometimes you can do some magic with analytical one. I'm not entirely sure here if you can get rid of any large circuit itself. So yeah, I don't know. Maybe you mentioned Nova and so on. So I just wondered if there was anything.
Yeah, maybe Nova could be one, like using folding scheme to.
Yeah, exactly.
Yeah.
To,
Yeah. If there's like a duplicate circuit, duplicate constraints, we might be able to do Nova kind of folding. Yeah.
So for the aggregator, is that centralized or decentralized? And what will happen if it is a adversary user?
The aggregator, so yeah, this is really theoretic at this point. So we still don't know if applications will require a decentralized aggregator or a centralized one could be sufficient. And there are some like other methods to posting things on chain, and we could play around with the trust assumption with like other with other design or something. But eventually, yes, decentralized aggregation could make sense. But yeah, we're still early, and we still don't have like this working yet. So yeah, it is a question, but it's going to be pretty hard in the future, I guess.
Okay. Thank you.
Thanks. So thank you. It's like a mix of a question and comment. You mentioned nullifiers, and I suspect that there are a number of projects in this area which need these nullifiers. And don't you think it would be an idea then to sort of come together and create a kind of ZK registry on chain that many projects could use at the same time, where people could just post some randomness or public keys or whatever they need to post?
I agree that a lot of applications will require nullifiers, and I think the registry idea is pioneered by the other solutions like Semaphore, which probably are using ZK-friendly, basically ZK-friendly curves. But in our case, we just don't want to have that kind of registry, but we could have it, but it introduces like this anonymity set complexity, and like users also have to manage their ZK identity, like have a wallet just for that. So that could eventually be like the industry standard. We still don't know, but we're just exploring this approach of using existing keys and enabling ZK proving. And using existing keys and using nullifiers, we need to, so for example, in an ECDSA nullifiers, we need existing wallets to adopt this new signing scheme, which only lets you generate a single signature for a particular message, or you can generate like two different, but if you ZK prove that, you cannot prove that the signature is unique. So we have this proposals, like it's basically an EIP for wallet implementers to implement this particular signature scheme that allows nullifiers for ECDSA. But we don't know if wallets will actually adopt that or if like that's the proper way to go forward. So, but yeah, it is a really important primitive, and without nullifiers, many applications can't be developed.
And then also in general, you don't necessarily need signatures from one scheme. It's enough to have just some randomness that the user can regenerate, and then that randomness can be used for many schemes. So it can actually simplify things. Okay, that's another discussion. Thank you.
In a blog post you released a while ago, you tried to optimize the proof generation by pre-calculating the results of some possible scalar multiplication.
Yes, yeah.
And I saw that it's 65 or so in numbers. I was wondering if that would reduce the entropy for it to become too vulnerable.
Oh,
What would you say to that?
I don't think so. We're just pre-computing the variables.
And you use it as a public input
Yes,
to
yeah.
the circuit, right?
Yeah.
And that would give some clues to some adversaries.
We include all of the pre-computes. We include all of the pre-computes, and we don't know which pre-computes are used in the circuit, so it doesn't reduce any like zero knowledge.
But given the number of pre-computes, like given the number of the results of the scalar multiplication, maybe the adversary could run, some possible permutations.
You mean like side channel attacks, or no?
Maybe I can ask later.
Yeah, we can discuss it later. Yeah.
All right, I would say let's wrap it up and head over to lunch. If you have more questions for Dan, find him on the lunch break. Thanks,
you.
everyone.